So what I'm going to do today is I'm gonna continue on what we did last time. We spoke last time about the first moment of area. Today we're gonna talk about second moment of area. But let me, in this first page, just quickly review what we did last lecture. So we spoke about the first moment of area, which has an equation. For example, if I want to find the first moment of area about x-axis, so I will say S of x, which is S is the first moment of area. I don't know why it's called S, but it's called S. And the S sub x, so the sub here is what axis you want to find the first moment of area about. So if I do have a shape, like this, for example, bless you, and here's this x. So this is what we mean with x sub x. If I have another, for example, axis here, and I called it u, and I want you to find the first moment of area about u, so I will say S of u. So it's important just to notice what the subscript of the symbol S is. And this is what tells you where you want to find your first moment of area about. So we said that S of x in the integration form, but let me tell you something, because if you read the book, some books symbolize it as S and other book as Q of x, okay? And then here is the mathematical form, which is integration y d area. But when I write integration here and d area, this is just for for the explanation point of view. I don't want you, when you solve problems, to do the integration. No, we're not doing integration. Instead, what we will do, we will say summation area times y. And same thing, area times y. Same thing, if I want to find the first moment of area about y, I will say sy is equal to q sub y integration x d area equal to summation area x. I know it's kind of confusing to say S of y, and then in the equation you will multiply by x. But basically, if you think of it, if I want to find the first moment of this area around x-axis, we need to find the rotation of this area about x-axis. That's why we take dy, because again, the application of this first moment of area to find the centroid. So if you remember what we did in the session, if I want to find the centroid, which is x bar, what I would say, I will say summation area times x over the summation area. And the summation area times x, let me break it up. I have a1 x1 plus a2 x2 plus until an xn over the summation of area, which is, let me write it down, a1 plus a2 plus until an, which basically tells you no matter how many division you divided the whole shape, you need to find the area of the first divided shape multiplied by the x. And x here is the horizontal distance from the centroid of the divided shape to the axis. We all practiced this last time. So the same thing with the y bar. I just want to write it down, and this is what I want you to write. I don't want you, when I ask you about the centroid, I don't want you to do any integration unless the shape is weird. But in this class, I'm not going to give you any weird shapes. Maybe in your advanced classes you will have some weird shapes. That's why I introduced the integration for you, and we just use the integration ones just for your knowledge, in case in advanced classes when you have a weird shape, and you're going to have that later, you know how to do the integration. Okay? So for y bar, it is summation area times y over summation area, which is again same thing here. And you can do that. You can just save the same equation in your calculator, but instead of x1 and x2 and xn, what would you have? The y. So if you're confident with your calculator, you can, I mean, I can teach you this in Casio, but probably your calculator can do that as well, which is you can symbolize the second term here, and then with one click, write these numbers, and with another click, you can write the y numbers. Okay? So it's not that hard. And one of the application also of the, or I already mentioned that, for the Sx is to find where the centroid is, because basically the first moment of area tells you the distribution of that area and how far is it from the axis that you're asking about. So we all agreed that, for example, in that shape that we set as an example last time, if I want to find the first moment of area of a shape, I have to find the centroid of that shape first. For example, if it's here, and I want to find S of x, then the area of that triangle multiply by this y. And basically, S of x gonna decrease when I move this axis until it hit the centroid. And when it hits the centroid, that's when we will find the S of sub u. And then you all agree with me it's gonna be equal to 0, because again, at this point, we have the area and multiply by what? What distance? Y, which what's the y equal now? 0. That's why S of u, and if I told you what is the first moment of area about a centroidal axis. So now u here consider a centroidal axis for this shape. So if you want to find a centroidal, if you want first moment of area of this centroidal u axis, that's gonna be equal to 0. And that's how we symbolize this. And instead of writing instead of writing integration y, we can write integration y bar, the area. And this y bar tells us, okay, the y bar, which is the distance from the small area, or this area, to u, that's the y bar, because we are relating now the distances to the centroidal axis. That's why when we derive an equation from now on later, when we integrate the first moment of area about the centroidal axis, that's equal to 0, and that's where you know, okay, we're already at the centroid. Tell me.
Are we still going to do summation, though we're not integrating that as well?
No, always, I'll not ask you to do an integration, because again, integration is summation. But I will put it to you in the simplest way that you will only have to do this guy.
With that equation you just wrote,
yeah,
we're going to do the same thing for just x and y bar as.
But again, this one you will not have this part.
No, I know.
This will be 0.
Yeah, it'll be different.
Yeah,
So it won't matter.
it would matter. Yeah, yeah. You had a question? Okay. Okay, now let's practice something. I have some rectangles here, and just to give you the sense of the S sub what. So x shouldn't always be at the origin shouldn't always be at the origin left point. This is a way I told you to put it to have the shape in the first quadrant, so you have everything in the positive. But let me tell you something. If I ask you the first moment of area of this shape and S of x, which is about x, so when you see x here, go look where the x is. This is why I just want to show you this example. I want you to practice. If I ask you S of x, look where this x is. So this x is here. So now I know that I will have a value, for example, for Sx, and same as Sy, I will have a value for Sy. The next one here, now I told you, find me the first moment of area about x. Okay, where is this x is? At the centroid. So will I get a value here? It's going to be 0. This one, the second one. Again, Sx is equal to the area times the distance from the centroid of that area to the x. Since it's aligned on each other, so this one is going to be 0. But I will have a value for Sy, because again, Sy is equal to area, or integration the area times x, because the horizontal distance to that y. So the centroid of that shape doesn't align with the y. That's why I will get a value here. I'll get a number here. Finally, or not finally. Same as here. Now I do have sy, and the distance x is going to be 0 because the x here aligns the horizontal distance, because with sy, I'll have x. So the horizontal distance aligned with the centroidal axis. That's why there is no distance to multiply the x with, or the area with, that's why it's 0. For sx, I will get a value. Finally, if I do have the both axes on the centroid, then both sx and sy gonna be 0. Is that clear? Tell me. Okay, and now, when I told you, okay, using this concept, which is, for example, if I do have this game, which you find it in the park, and I told you place this triangle or this support in a location where it can be balanced, although I do have different masses, which is 10 and 5, but we can play around with this by increasing the arm distance. So if I increase the arm distance of the 5 kilogram, that's how it's going to be balanced. So we introduced the concept of the mass time distance can give me a resistance in terms of moment arm, which is in different word. If I do have 10 kilograms here, and I want to put something like some weight here, less weight, and with a distance, how can I resist this 10 kilogram? And by resisting here, I mean to make it balance. We said, of course, if we do have 10 kilograms, or I do have less kilograms, which is 5 kilograms, I can play around with the distance. That's how I'm increasing the moment arm. That's how I'm getting a resistance. So then we went through a derivation process where we found the moment to the left is equal to the moment of the right, and we cancel all the masses. And an important condition here that to derive the centroid and the first moment of area, and later now the second moment of area, we need to have a homogeneous cross-section, which means the cross-section should have the same material, same thickness, which is the same, for example, as span of a beam, and that's how these equations going to be valid, because we found that the density canceled each other, the thickness canceled each other. In next lecture, we will have two materials. That's when all these equations are going to be valid. So it's important how we derive the equation, what terms we use to derive the equation, because if we played with or we changed the basics or the terms, the equations are no longer valid. And then we did an integration to one of these shapes, and we said we wanted to find the moment of area about, for example, centroidal axis, and how we found out it's 0. The reason why it was 0, because whatever strip we take here, with a distance y, for example, there was another strip here with a distance of negative y. That's why the first moment of area about the centroidal axis was equal to 0. And the first moment of area is area times distance, so it's inch power cube, for example. And I've been asked, okay, what is the physical meaning of inch power cube? Is it a volume? No, it's not a volume. It is just, it's a new thing for you now, and just program yourself on that. The inch power cube here doesn't mean volume. It does mean the distribution of the area relative, or how far is that area from the axis of bending, or the centroidal axis. And then we introduce something, because we want to use this idea of if I change the location of that area, or how, like if I put the area way far from the center, I'm getting a very strong resistance. That's why the 5 kilogram, when I put it in a way far distance, I get the same as 10 kilogram. But we wanted to generalize this concept, and we couldn't do this because the first moment of area about centroidal axis was equal to 0. That's why we said, okay, what if instead of integration y d area, this is the first moment of area, we raise the power by 1, so we have the integration of y squared. And this is a new term we have here. And this is the moment of area, the second moment of area about x, which is basically the moment of inertia. Or it's also called second moment of area. And the reason why we call it second, because we have power 2. Okay? And the same thing, if I want to find y, Iy, it is integration x squared d area. And now let me go ahead, and it's the same thing as what we did in the first moment of area, only the difference is this is power 2. And what is the moment of inertia tells me? This tells me the resistance of that shape. The resistance of that shape to bending or to rotation. And because it makes sense, if I do have this steel bar, it's made out of steel. There is a stiffness due to the material because it's steel. Because if I have this material and that material, if they have the same shape, of course the steel gonna be stronger or stiffer. So we have something we call stiffness due to the material, which is symbolized in the elastic modulus, which is E. And then we have something which is, if I do have now this steel bar, so same material, and I increase the cross section, although they are steel, both of them has the same stiffness due to their material, but now I do have another stiffness which is due to the shape. So now we are introducing two things. At the beginning, we do have a stiffness of a material due to, a stiffness of this beam due to the material, and then we have a stiffness of the beam or this material due to its shape. And due to its shape here is represented in Ix and Iy, which I'm going to explain further. But Ix and Iy again, it is the resistance to bending. Okay? So Ix, Iy resistance to bending, and then let's derive the moment of inertia for this shape, for example. I know some of you might know it, but let's do the integration once so that from now on, I will just put down the equation. I don't have to every time do integration. We will do it once, get the moment of inertia for the rectangle, and we memorize it from now on until you retire, because the rectangle shape is very popular. So let me do the Ix. Let me do the integration for Ix for that shape. Okay? Let me make it closer here just to see it. So what do we have? We have integration y bar, d area. So y bar here is the vertical distance. That's what we want to integrate about. And then here is the strip that we're going to move throughout the area. And throughout what area? Which has a limit integration from negative h over 2 to h over 2. So basically, we want this strip to move all the way down to all the way up. That's the integration that we want to take this about. And I'm going to set this equal to y, this distance y, to indicate it's a variable. Okay? And again, if you remember what we did in the first moment of area, the dimension of that strip, which is the d area, if I want to find the d area, which is the area of that strip, the horizontal dimension here is b, because that's the width of the beam. And the thickness here, I'm going to call it dy. Therefore, d area is equal to b dy. And I'm going to reflect that in the equation by saying integration again, h over 2 to h over 2, negative to positive, and then y squared b times dy. But since b here is a constant, I'm just going to take it out of this integration, and this is the integration. And if you remember, when we integrate something, we raise the power and we divide over the new power. Therefore, I will do have b is equal to y power 3 over 3. But again, 3 is also constant, so I will put the 3 outside. And the limit of integration here is from negative h over 2 to h over 2. Lastly, b over 3, I will have h over 2 power 3 minus negative h over 2 power 3, which you will end up with h power 3 over 8 minus minus, which is plus h over 3 power 8. What is that now equal? b h cubed over 12. So for a rectangle section, if I want to find the moment of inertia about x-axis, what you want to do, you want to say b times h cubed over 12. Okay, this is how we do the integration for it. I have a good way to memorize this, and I've been using this since forever. Now I wanted to make sure that you understand how we derive it. Now let's do some shortcuts or how to memorize all this using like the shortcuts way. So if I do have this rectangle, and I told you what is the moment of inertia of this rectangle about x, what I want you to do, I want you to memorize this by heart for only rectangle and square. So the moment of inertia is equal to parallel perpendicular cube over 12. What I'm saying here is, if I'm asking you now, what is the moment of inertia about x, what is the dimension that's parallel to x? What is the dimension that's parallel to x? B. So you want to put b here. What is the dimension that's perpendicular to x? H. So you want to say bh cubed over 12. So that's if I want to find for ix, and now for iy, now you tell me, parallel perpendicular cube over 12. Always memorize this. I mean, I just translated from Arabic to English, but in Arabic, it's like there is a symphony when I say it, but in English, it's a little bit hard, but I think it makes sense. So parallel perpendicular cube over 12. So what is parallel here to y? 8. What is perpendicular to y? b cubed over 12. Okay? So what does the equation tell me? Tells me if this shape gonna bend about x-axis, so this is a cross-section, if it's gonna bend about x-axis, this is the resistance of this shape to that bending, which also tells you, okay, the higher the I, the more the resistance you're gonna get. And you're gonna see in this equation, what is dominating here in the equation, it is h. Which tells you also, if I want to have, for example, if this is a beam, if I want to have this beam very strong in resisting the bending from the people who are above us, we need to increase its thickness. Because if we increase its depth or thickness, we're gonna get a high, like we're gonna get a moment of inertia to the power of 3, more than if you just increase the width. So increase the width, it's also gonna affect in the inertia, but not as much as the h. That's why in some application, when you want to increase the resistance to bending, we increase the h. But sometimes the architect, and it does make sense, I want to increase the stiffness of that beam, but I can't increase the h like forever. Because again, you guys gonna be disturbed and the architect gonna be disturbed because it's now gonna like obstruct the view of the board. That's why now sometimes you'll find a beam with a very large width. That doesn't make sense, but again, we have no choice. Okay? There is nothing to do but to increase that width. So if you have the luxury to increase the height, you're gonna get more stiffness, but this luxury not always there. You always have a limit. Okay? So now, for each shape, any shape, I'm just like practicing on a rectangle, and whatever goes on a rectangle is same as a square. But for each shape, we do have ix and iy, which is the properties of the shape itself. Again, I'm saying ix, iy because that's how most of the beams are. So the beams are, or let me explain this later, just not to confuse you, like in the next couple of slides. So now if I want to find, if I do have a shape, or I do have a cross section, with this given dimension, let me give you a sense of how strong the ix relative to y. So you all see that I do have 60 as a height. So I want you by default to in your mind, okay, now I know if I have a height like this, so that means the ix is way larger than iy, because the height in the height perpendicular to x is larger. So the height or the dimension that's perpendicular to the axis always tells you which axis is stronger. So now if I want to find Ix, I will again use parallel perpendicular cube over 12. Dimension that's parallel to x here is 20. Dimension that's perpendicular to x here is 60 cube over 12. And this is going to give me 360,000 inch power 4. Again, inch power 4 doesn't have any physical meaning. It's not a volume or not like a 4D thing. It is just now inch power 4 is an indication of a resistance to bending. Okay? So now I do have Ix is equal to that. And now I have Iy, again, parallel perpendicular cube over 12. That's why it's important to always read the subscript. So the subscript here tells you y. Go read where y is here. So y is at the centroid. So now I want to find the moment at the centroid. So now I will have 60, which is parallel to y, times 20 cube over 12. And this will give me 40,000 only. Which tells you, and it does make sense, which tells you the resistance of this shape to bend about x is way larger than the resistance about y. That's why whenever you know an axis that's stronger than the other, we call it strong axis. So x here, we call it strong axis. And here is a term for, this is a term just, we use it in practice and perhaps in the academia here, for example, in the exams or anything, it tells you, put your beam in a way that it will resist in its strongest axis. Because again, I told you sometimes I do have a beam like this with a very large width and a very small height. So we align this beam now in its weak axis. Okay? Again, I will just have you practice this concept in this loads. Okay? And when you know the strong axis, of course, the other axis is going to be weak axis. So let's practice what I just said here. So if I, tell me.
So with units, with the moment of inertia, do we, because you said there's no kind of physical representation of it.
No.
Can we use like typical unit conversions then if you wanted in like feet to the power 4?
Oh yeah, just multiply by the conversion. It depends on what dimensions, because I gave you here centimeters. Oh, that's my mistake. I see what you're asking. Oh, my bad. This should be centimeter power 4. And of course, if I gave you centimeter here, that means centimeter power 4, inch. And it depends on the equation, maybe because later this I, which makes sense, is going to be in the bending stresses, which tells you how the shape going to bend. Because again, this is a resistance to bending, so it has to be in the stress equation. So you are right. If the stress equation, everything in inches, so convert everything in inches. But I'll not give you a question that I will ask you to convert from SI units to English units. That's rough. I'll not do that. Within the, for example, the SI unit itself, I will ask you, for example, centimeter to meter, inch to feet. That's all. Okay? Okay, the load here. So if you do have a, if I ask you, okay, now I do have a horizontal load, and this is what we practiced before. This horizontal load will cause the beam to bend about what axis? Y-axis. So now we know the axis of bending is Y. Once you know the axis of bending is Y, so we want to design this beam to be strong in the Y, in like to resist the Y bending. Okay? So now, what do you think, which shape? So I do have a cross section, same dimension. How gonna we rotate it in a way that it will resist this? Anyone? So is the first one or the second one? That was quick. Anyone suggest the first one? Okay, the reason why it's not the first one, because if you look here, now I know that it's gonna bend about Y. So I need to have the Y to be now a strong axis. But now I do have Y here is weak. That's why I need to rotate it in a way that the dimension that is strong is parallel, for example, to the load. Okay? So that's correct. This one we would choose most of the times. I don't want to say all the times because we go down to this one, this vertical load. What is the more effective way to align this beam to that load? The first one. The reason why I'm telling you not, I mean like, the reason why not most of the time we put it that way, but sometimes we put it that way, which is same as this beam above me. The engineer couldn't increase the height of that beam. He only was able to increase the width. Of course, that's a waste of a material that cost him so much. This will cost him less, but he had no choice. The architect perhaps told him, and it makes sense, you don't want me to stand and like there is a beam above me like this. You'll not see the board, okay? But again, increasing the width is effective, but not as effective. So here will be the width. Not as effective as engineering, like increasing the height, okay? So if you all know, most of your homes are made of wood. So wood is like a very weak material in terms of the modulus of elasticity compared, for example, to concrete and steel. But the engineers know how to align the cross-section to benefit from the stiffness of the shape. Okay? So if you know how to align your beam, you're gonna get advantage. I mean, you can now use a lot of wood, yeah, but it's a weak material, but it's important to know how to align this material relative to the load. If I do have a gravity load, gravity load means like us as humans and the dead load, you wanna place your beam like this. But from the outside, you do have wind. So it's important the outer beams, at some point in the outside of your building, you wanna place it that way. And whoever went to the gym, you're not gonna find all the beams that's like at the wall, not all of them looks like this. Some of them look like this. It's placed that way so that it can resist the wind that's coming on the building. Especially that we have a very big facade at the gym. So imagine all this wind pressure in that area. So multiply the area times the wind load, so you have a very strong loads. That's why it's important to place the beams like this. Okay? And not only in the gym, like at any building, usually we do have at the perimeter or the circumference, we do have this kind of alignment. Okay? So what I did now, I did the moment of inertia for the rectangle shape, and whatever goes on rectangle goes on triangle. But I want you to notice something. How many axes do we have here? We have x bar, and we have x. Yeah, we have x and x bar, y bar and y. That's why you will have ix, iy, and then ix bar, iy bar. So it's important that you notice that this ix, it is the moment of inertia about a centroidal axis, ix and a yy. But ix dash and iy dash, that's the moment of inertia about another axis, which is this axis. Okay? So it's important to know what axis you want to, and therefore choose your equation. And again, you can derive all these equations, but yeah, you can do it at home. But like what we are interested in is rectangle and square for this class. Okay? I don't want you to memorize anything of those or derive them, or if you want to do just for your knowledge. So let me move now to something else. If I do have this shape, and I do have two axes, x bar and y bar, and then x and y, and I want to find, let me put it that way, and let me erase those axes. Now I want to find the moment of inertia about the centroidal axis here. Okay, it was easy. For example, for ix, it is bh cubed over 12. And for iy, hb cubed over 12. No, it's not going to be 0. The first moment of area is going to be 0, not the second. And again, remember, the reason why we use the second moment of inertia to have the y squared in the integration so that the negative not going to cancel each other. So this one not going to be 0. The first moment of inertia is going to be 0. I'm not asking you about the first, I'm asking you on the second moment of area, which is the moment of inertia. Is that clear? So let me ask you something. Now if I do have this shape, we're gonna divide this shape, for example, to two shapes that we know their properties. And now I ask you, what is the moment of inertia? Let me erase those first. What is the moment of inertia, for example, about the centroid of that shape? And centroid of that shape is going to be somewhere here. This is what you did in your in-class assignment last time. Somewhere here. So let me tell you something. So is the moment of inertia, for example, about x going to be, I have two things. So I have moment of inertia about x for shape 1 and moment of inertia about x for shape 2. Will that be, for example, bh cube over 12 plus bh cube over 12? Of course, b and h here for each shape. Is this correct or no?
No.
Why is that?
Because one of the parallels to x is going to be greater if it's the opposite.
That's right. So here is the point. If I do have the centroidal axis coincide with the centroid of that shape, then the moment of inertia is bh cube over 12. But when the centroid of the shape, which is here, for example, for shape 1, when the centroid of the shape doesn't align with the centroid of the whole shape, that's when this equation is not enough. And what we need to do, we need to find this distance, that's how far this area is away from the centroid of the whole shape, and then we will add additional term, which is the area of that one plus d squared. And let's derive this now. But the whole point of showing you this is, if the area, and that's the what we call parallel axis theorem, which is if the centroid of a shape doesn't align with the centroid of the whole shape, that's when bh cube over 12 is not enough, and we need to add another term, which in other words, we need to add another term which will increase the resistance to bending of that material, which also introduced you a concept of the further we put the material away from the centroid, the stronger the material gets. So let's derive this, and I will show you application in a moment. I do have this shape, the same rectangle again. What we did a couple of slides ago, we found the moment of inertia for the centroidal axis. But now I want to find Ix, which is now the moment of inertia of that shape relative to that axis. Okay? So what we do, again, same thing. We will have this small strip, and then I will rate that strip to the centroidal axis of that shape. And I will call this y bar. Okay? So this y bar gonna increase in the positive x bar, and gonna increase also in the negative x bar. So it's this strip gonna go up and down within that area. Again, the equation for Ix is equal to integration y bar d area. And now y bar here, which is now this y, okay, because I want to find the moment of inertia of this shape now around x. So that's why I'm taking that y. So that y is equal to d plus y bar. Do you all see it? Okay. So now what I want to say, y bar is here is equal to d plus y, and now the whole y bar, and now the whole thing is going to be squared. Okay? Just let's break this equation. We have d squared plus 2 dy bar plus y bar squared. And this dy, d here is distance, so this is a constant. This is not like a d area here. This is just a constant. And if I want to use the properties of integration, if I do have addition, I can separate the integration, which is d squared d area plus 2. And I'll put the d out because, again, d is a constant, because that's how far the distance from the centroid of the shape to the centroid to the axis of reference, which is this d. So I have this d, which how far the shape is, of the centroid of the shape is relative to the axis. And then this is constant. And then I have 2d integration y bar d area, plus lastly integration y bar d area. Let me put it in a way, and I will have you to tell me what each one is. Okay? 2d, I just put the d out because d is a constant, plus integration y bar d area. Now I want you to tell me what is Ix equal for this shape around x-axis. Now tell me, what is the integration of 1 dA? A times what? D squared. So that's the first term. Second term. 2d times what? So this is the integration of y bar, right? Is this the first or second moment of area? Integration y, which is the integration of the first moment of area of this shape around its centroidal axis. What is that equal? So I will not leave here until you guys tell me, because this is what I was introducing to you since last time. That's why I'm like always showing you integration, so that when we derive any formula from now on until the end of the semester, I want you to just notice all what this integration tells you. So, okay, let's start with that one. Integration y squared dA, what is that? This one, the first one? Okay, this one is 2d times integration y bar d area. Integration y bar d area, is that the first or second moment of inertia first? That's first. And when we say integration y bar, that is as if s of x bar, which is the first moment of inertia about the centroidal axis. What is that equal? Okay, 1 minute, let me show you. Okay, this is the shape. I do have x and y, and I do have x bar and y bar. The first moment of area of this area around its centroidal axis. What is it? Thank you. Genius. Genius. Do you all agree with him? We practiced that at the beginning here when I told you what is the first moment of area about its centroidal axis. That's why it's 0. And finally, what is the integration of y bar squared d area? No, I don't want you to integrate. I want you to tell me what this symbolizes. Moment of inertia about which axis? Is it x? Because I do have two. I have x and x bar. Which x is this? X bar. So now, if I want to find the moment of inertia of x, which is an axis that doesn't align with the centroidal axis, what I would do, I will first of all find the moment of inertia of the centroid axis, which is bh cubed over 12 here. And then I will add another term, which is the area times d squared. So the area of that shape times the distance squared. Okay? Same as Iy, then Iy bar plus area, and then d squared. And this d now gonna be here, for example. Let me call it dx, and this is dy. dy dx. Is that clear to everyone? Okay. Now, let's relate to what we did before. What we said now, if I do have this area, okay, and if I want to find how this area gonna rotate about y, about x, that's why I'm multiplied by y. So that was Ix, right? Which is integration y bar d area. And then if I want to find how this shape gonna rotate about y, so I multiply by x, that's the moment of inertia about y, and this tell me Ix tells me the resistance of this area when it rotates about x, which is rotate about x. And now when I say Iy, the rotation of this area around y. But what we are missing here is if I do have an axis here, and then I do have x bar and do have y bar, now I do have rho square. And rho square now, it tells you the rotation of this shape around the z-axis. The rotation or the resistance about z-axis, what was that? Anyone? No, what? I mean, what resistance does that represent? So Ix, resistance of bending about x, Iy, resistance of bending about y, Iz, resistance of bending about z-axis. So resistance of this about the axis. What was that? Do you remember using it before, a couple lectures ago? That's torque. Do you remember the J or Iz, which is integration rho square d area? This is what we used when we wanted to find the resistance for torsion, for example. Torsion is also rotation, but it's not rotation about x or y. It is rotation for this shaft, for example, about which axis? Z. That's why when I have integration of rho square d area, that's give me the resistance to rotation. So for any rotation inertia, you have to find the respected inertia in the stress equation. So in the torque equation, or in the shear stress equation due to torque, we had J in the equation. For example, T R over J, or in the deflection, TL over JG. And in the bending stresses, we're gonna find also the Ix and Iy. And if you remember that J now, because this is rho square, and if you want to do the triangle, rho square is equal to x squared plus y squared, right? So if we want to find J another way, it is Ix plus Iy. Because basically, the integration of rho square is equal to x squared plus y squared from Pythagorean theorem. And if we do the properties of integration, I do have integration x squared d area plus integration y squared d area, which is Ix plus Iy. Is that clear? So we are now just like trying to connect everything together, just to make sure that everything makes sense. Okay? I don't have time to go through, I mean, this is what I explained. I don't have time to go through an example. I will do that in the end class, but let me tell you the application for this so that you would appreciate the moment of inertia concept. So I do have a cross section like this. That's why you will always find, for example, the I section. And I section here is basically what we are doing. We're just like throwing the area away from the centroid, okay? To take two advantages. The first advantage is in the inertia, we have bh cubed over 12. So I have the height cubed. In addition, I do have the advantage of bh cubed over 12. The advantage of this area times its distance square. So if we put the area away, we're going to get advantage of how away it is. That's the first thing, which is the h cube. And then we're going to take advantage of the area is away, so area times distance square. That's why sometimes when they do have a cross section like this, what they do, they go with the laser. So just like a way to increase the h, and you're going to find this in a parking garage. Look at this, it's very cool. What they do, they go with the laser cutter here and just cut it. And what they do, notice, now I cut it, and I'm putting it that way. What did I do? I increased the height, okay? And I increased also how far the areas are. And in addition, I allow the holes here for just electromechanical people to put their stuff. So this picture, I was so glad I took this picture in New York. I was usually using it for my slides, but I found it and I was so happy to see it. But do you see how is it, and do you see how all these pipes can go through? So I increased the height. I added a hole so that the pipes can go through. Of course, there will be like an extra stresses be added, but I have a very strong resistance, especially in a garage where I do have a big cars. And in bridge, for example, when I do have bridges with like a very strong loads, and I'm not interested in the materials that are gonna be located in the middle. If I want to manage how I distribute the material, like a resource allocation, I will put the material away from the centroid. That's why it's useless to put any material here. The only material I'll put it here is just to connect the two sections together. But last thing before I close this lecture, I'm 1 minute, okay, is I'm telling you to put the material away from the centroid. That doesn't mean that you will make me a cross section that is a very thin like this and put it away. Theoretically, you will have a very strong bending if I give you material and told you just to allocate it. If you put me like a very infinitesimal section in the middle and put everything at the end, yeah, you will have a very strong bending stress. But this will fail right away in a shear stress, which we're gonna discuss next week. Okay? So that's why we need to study the bending stress, which is next lecture, and then shear stress, which is next week, so that we can combine them together just to know now what are limits to design our cross section. In the session, we're gonna practice the moment of inertia by using this example, and then I will have you to practice in the session. Any questions? Okay. Hello again. So I'm gonna continue what was left from the lecture. It's just 2 slides. It's an example, and then here is just like a review on what we did. So if we do have an area like this, and I told you what is the moment of inertia, for example, about, I would say, x, for example, or y, here I want you to use the equation I, x, for example, will be bh cubed over 12, and iy will be h b cubed over 12 only. Again, I use this equation bh cubed over 12 or parallel perpendicular cube over 12 because the centroid of this shape coincide with the centroid of the whole shape because they're both one, okay? Unlike this example, for example, if we have an I section, what we will do first, we will divide this I section to an areas that we know where their centroids are. So I will name this 1, this is 2, and this is 3, for example, okay? And then I know that the centroid of the whole shape, of this entire shape, is gonna be in the middle. And I don't need to calculate the x bar and y bar because I know there's the symmetry about x and I know there's the symmetry about y. So in the middle here, that's the centroid of the whole shape, okay? So now I do have x and I do have y, which is the centroid of this whole shape. So now, if I want to find the moment of inertia, I do have 3 shapes, I1 and I2 and I3. Let's say, for example, I want to find Ix for this whole shape. So I will say I1 plus I2 plus I3. 1 and 2 and 3 here, that means 1 for area 1, 2 for area 2, and 3 for area 3. So what I will do for I1, I want to first find what is the centroid of area 1. So the centroid of area 1 is right in the middle here, okay? This one. So if the centroid of area 1 doesn't coincide with the centroid of the whole shape, then bh cubed over 12 is not enough. I need to add another term, which is the area 1 plus this distance, okay? And it's gonna be squared. So if, let's for example say that this dimension is, let's say b, and this is T, for example, same as the bottom one, T, and here is B. So area 1 is going to be around X, which is parallel, which is B, T cube over 12, and B and T, they are the B and then T cube over 12, and then plus the area 1 times the distance 1 squared, and this is the distance 1. Okay? So this is the first term, which is I1. With a different color now, I want to find I2. So now notice that I2, the centroid of I2, coincide with the centroid of the whole shape. That's why I can say that BT cube, no, I didn't give a dimension, so let me say this is, for example, this dimension is C, for example, just like using any symbols here, and the height of it, let me call it M. So the moment of inertia now will be, for area 2, is going to be C M cube over 12. Is that enough? Yeah, that's enough for area 2, because because the center of area 2 coincides with the centroid of the whole shape. So there is no A1 d square. Because if you think of it, and if you forgot and you added AD squared here to area 1, so the d here is 0. That's why the second term, it's going to be 0. That's why Cm cube over 12, that's the moment of inertia for area 2. And now area 3, I will say BT cube over 12, which is BT cube over 12, and then the centroid of this shape 3, doesn't align with the centroid of the whole shape. There is a distance here. And let me call this distance, for example, distance 2. So I will add area 3 and then distance not 2, 3 squared. Okay? And that will be the moment of inertia. Two different shapes and, of course, two different moments of inertia. Okay? And finally, let me solve now an example. So now I'm asking you, what is the moment of inertia about Ix dash and Iy dash? So you need to know where is the x dash and y dash. So x dash and y dash are here. So now I want to find the moment of inertia of this shape around x dash and y dash. And that's usually what we do. We always find the moment of inertia about the centroid of the whole shape. And how do we find this? We did it in the last lecture, same example. We found the x bar and y bar. And when we find the x bar and y bar, that's where we're going to take the moment of inertia about. So let me start first, but let me put some dimensions here on the graph. So the 7.35, this is what you all calculated. This is the y bar. And the x inches, that's the x bar. Okay? So let me now put on the diagram. So for area 2, I know the centroid of area 2 is here. And if the whole height of area 2 is 8, so half of it is 4. And I'm relating now everything related to the reference axis, because the x bar and y bar we measure them from the reference. That's why the centroid of area 2 is from the reference. The centroid of area 1, we're going to measure it from the reference. So I'm going to call this y2. And this is what y2, we used it in the centroid equation when we multiplied the area times like a2 y2 plus a1 y1 in the numerator part. And for area 1, this distance, I'm going to call it y1. And this y1 is equal to 8.5 inches, because this is 8. From here to here, that's 8. And then if the whole thing is 1, then half of it is 0.5. That's why the whole thing is 8.5. So let me do first Ix. So for Ix bar, I do have inertia for member 1, and I do have inertia for member 2. So inertia for member 1, always the inertia is parallel perpendicular cube over 12. And then that's always there. That's the first term that's always there. The plus area times d square, that's not always there. So let me write the parallel perpendicular cube over 12, and I do have here 12. The thickness here is 1 cube over 12 plus. Plus here is the area times d squared. And now I will look in the graph, and I will see whether I need the second term or no for the moment of inertia of shape 1. And when I looked, I found the centroid of shape 1 doesn't align with the centroid of the whole shape. That's why I need to add the extra term, which is area times d squared. So what is the area one? It is 12 times 1, and then times d squared. And d squared is basically this distance from the centroid of the shape 1 to the centroid of the whole shape. Let me call it d1. How do we find d1? So d1 is simply the subtraction of the centroid of the whole shape, centroid of shape 1 minus the centroid of the whole shape. So if you know, and it always works. So it's always y1 minus y bar, or y bar minus y1, doesn't matter because the whole bracket is going to be squared, d squared. So always y1 minus y bar, okay? This will give you your distance, which is, let me write it here, 8.5 minus 7.375, and the whole thing, the d squared. So now I finished the moment of inertia for shape 1. Okay? And the d squared here, so d squared is equal to y minus y bar square. And here is, I will put yn, which indicates the whatever area that I'm working with. Okay? So now let's do the moment of inertia 2. So plus the moment of inertia 2. So moment of inertia 2, which is for area 2, about x bar. So now I notice that the centroid of area 2 doesn't align with centroid of the whole shape. So now I want to find this d, which is this distance. I'll call it d2, which is how far the distance from the centroid of the shape 2, to the centroid of the whole shape. So let me start first with the first term that's always there, which is parallel perpendicular cube over 12, which is 0.5 times the height of member 2. I don't want any of you to take y bar, because that's not the height of member 2. Member 2, the height is 8. So I will say 0.5, 8 cube over 12 plus the area, which is 0.5 times 8 times d squared. And again, d squared is yn minus y bar, which is in our case here y1 minus y bar. So what was, no, y2, sorry. What was y2? y2 was 4 minus y bar, which is 7. So 7 minus 4 is gonna give me that distance. So 4 minus 7.375. So the d is squared. So it doesn't matter which one you subtract from each other. So 7.375 minus 4 or the opposite. Doesn't matter. We want just the difference. And this difference is going to be squared anyway. So the sign doesn't matter. So if we solve this, we're going to find 83.083. Now it's important to write the units. The units of the inertia is inch to the power 4. Okay? So now I finished Ix, the moment of inertia about x dash. And now I want to find the moment of inertia about y dash. Okay? Y dash is here, right? And again, when I told you, when we got the Ix, I was asking you, does the centroid of any of the shapes align with the centroid of the whole shape? And the answer here was no. That's why we took the d. But I wasn't accurate when I told you the centroid of the shape align with the centroid of the whole shape thing, because when we talk about x, when I say the centroid, I mean, does the x bar of the whole shape align with the x bar of like the single shape that I'm studying? If no, that's when there is a distance between them. For for y dash here, does the centroid, for example, the centroidal y, which is y dash, the centroidal axis align with area 1 and area 2? The answer is yes. So the centroidal y of shape 1, for example, which is going to be here. So this will be x for 1, and this will be y for 1. So y for 1 aligns with the y for the whole shape. So now there is no d between them, because when we talk about iy dash here, so iy dash, which is the moment of inertia about y, which we are interested in the horizontal distance, okay? So now y dash, or the y for shape 1, aligns with y dash. That's why there is no distance for both area 1 and area 2. Therefore, the moment of inertia for shape 1 and shape 2 will equal to, for example, let's work on area 1 first. It will be parallel perpendicular q over 12. The dimension that's parallel to y dash, that's 1 perpendicular is 12 cube over 12 plus, that's for area 1. And again, there is no a times d square. And the reason why, again, because there is no d square in that direction, because y, the centroidal y of shape 1 aligns with the centroid of the whole shape, okay? For shape 2, it's the same thing. So I will only say 8 0.5 cube over 12. And the answer here is 144.08 inch power 4. Now you notice that iy dash is larger than the ix dash, so the stronger axis here is y, and the weaker axis here is x. So it's better, if we want to use this cross section, we want to apply a load horizontally so that this beam gonna bend around y. And if it's bent about y, that's when we're gonna see a higher resistance to bending. Okay? And that's all what I have for today, and I will see you tomorrow.